All right, y'all. Today we're going to be going a little bit deeper with our rational functions and talking about the zeros and using some of those zeros to solve rational inequalities, just like we did polynomial inequalities. It's important to remember that rational functions are really just two polynomials. If we have a rational function, f of x equals g of x over h of x, then we know that f of x has zeros when g of x is equal to 0, because that's just like any other polynomial functions. Whenever those factors on top are set equal to 0, we get 0. But what's a little bit unique about rational functions is that we will be undefined when h of x equals 0. Because when h of x equals 0, we would be dividing the rational function by 0, and we can't have that. We talked about last class how that is undefined. So we're going to use this to solve some rational inequalities. And importantly, we need both the zeros that come from the numerator and the undefined values that come from the denominator. Now, I'm not going to read all those steps to you. You can read those steps. We're going to jump straight into example 1. I'm going to kind of work through these steps as we see them. So let's look at this example 1. We want to solve the rational inequality x minus 2 over x plus 3 times x plus 6. Okay, and the first thing we want to do is we want to find our zeros from the numerators and our undefined values from the denominator. So let's go and set each of our factors equal to 0. So in the numerator, we get x minus 2. Pause real quick. In the numerator, we get x minus 2 is equal to 0, which gives us x equals 2. And then denominator, we get x plus 6 equals 0, which gives us x equals negative 6, and x minus 3 equals 0, which gives us x equals 3. Okay, and once we have all those zeros, we're going to go ahead and set up a number line just like we would for our polynomial inequalities. And then on that number line, we're going to put these same zeros in order. So negative 6, 2, and 3. But what's important to remember about rational functions, because if you don't already notice, this is greater than or equal to 0. So typically, when it's greater than or equal to 0, when we get our intervals at the end, we would want to include any endpoints where we could also equal 0. But any of our factors that we solve out of the denominator are going to give us those undefined values. So even if we have that equals 2, we can still never actually equal those. So what I'm going to do is I'm going to add a little undefined under our negative 6 and our 3, just so that we don't forget that our function is undefined there. And in fact, instead of under, I'm going to put it on top, because on top is really what we're putting our y values for our positive and negatives. And we'll put a 0 here on top of 2 to know that we do actually equal 0 at that 2. Okay, now just like we've done before, y'all, we can pick some values in between. So f of negative 7, f of 0. Unfortunately, this one's a little gross, so we'll have to do like a 2.5. And then f of 4. And then once again, we can plug these into our function. So f of negative 7 would equal, and I don't have to do all the math, although sometimes you might want to just do all the math to be safe, but I really just care about this being positive or negative. So let's go ahead and plug these in. So negative 7 minus 2 over negative 7 plus 6, and negative 7 minus 3. That would give me negative 9 over negative 1 and negative 10. So negative makes a positive on the bottom, dividing a negative number. That would give me a negative for my first area. So negative for f of negative 7. Okay. Same thing plugging in f of 0. Give me 0 minus 2 over 0 plus 6 and 0 minus 3. That would give us negative 2 over 6 times negative 3. That would be a negative over a negative, which would give me a positive for that one. Okay, plugging in 2.5, which I already see I'm going to run out of room, but it's fine. Hopefully y'all are writing smaller than me. 2.5 minus 2 over 2.5 plus 6 over 2.5 minus 3 equals 0.5 over 8.5 over negative 0.5. Positive and positive, but a negative would give us a negative for that one. So we're negative in our next interval. And then last but not least, f of 4, 4 minus 2 over 4 plus 6 over 4 minus 3, which would equal 2 over 10 times 1, which would give us a positive for our final interval. Okay, so we have our number line set up. So now all we need to do is we need to go and take this number line and write into our final solution, which our solution is going to be any values where our function is greater than or equal to 0. So that's going to be any values where we are positive, as well as any endpoints where we do equal 0. So noting on here, we can include negative 6. We can include everything between negative 6 and 2. We can include 2 because we equal 0 at 2. That came from our numerator. Then we can include 3, but everything greater than 3 all the way out to infinity. So for our solution, it would be not including negative 6 to 2 included in union with 3 not included to infinity not included, because we never include infinity. And that's really all there is to it, y'all. It's the same exact skill as polynomials, except two things. A, you have to remember to get your factors from both the numerator and the denominator. And B, when you're writing those inequalities, you just have to remember which factors were zeros and which were undefined, because that's going to affect your includes or not included in your intervals. Okay, so this is relatively straightforward. I do want to do at least one more with you though, and then I'm going to let you practice them on your own. Okay, so let's look at example 2. And right off the bat, hopefully you notice example 2 is a little different because example 2 is not factored for us yet. So since example 2 is not currently factored, we have to factor it first before we can do anything else. So on the top, x squared minus 4 would factor into x plus 2 and x minus 2. And on the bottom, x squared minus 10x plus 25 would factor into x plus 5 and x minus 5. And that, of course, is still less than 0. And I didn't talk about this earlier, y'all, but one of the key things to always keep in mind when we're doing these is that we're not getting any factors that cancel out. We shouldn't see any of those today. They will lead to another feature of our graph, which you may remember from Algebra 2. We're just not going to get into today. But we don't want to have anything that cancels out. That creates a whole nother situation we have to worry about. Okay, but now that we have everything factored, we can get our x values. So we get the x values of negative 2 and positive 2 from the numerator, and negative 5 and positive 5 from the denominator. So then setting up our number line, we have negative 5, negative 2, 2, and 5. And just like we did before, I want to go ahead and note our negative 2 and 2 come from the numerator, so they are zeros. And our negative 5 and 5 come from the denominator, so they are undefined. Now, on this one, not as important because we have that less than sign. So we wouldn't be including any of our endpoints anyways. So we don't have to worry about that. But we want to get in the habit of it anyways, just in case. Okay. And then once again, we want to plug in some numbers. This one's a little nicer to us on the number side, but we have to do 5 because we got 4 zeros. Let's do -3, f of 0, f of 3, and f of 6. So plugging these all in, f of -6. See, and I'm going to see if I can do my math a little bit quicker this time. So plugging in -6, -6 plus 2 would give me -4. -6 minus 2 would give me -8. -6 plus 5 would be -1. And -6 minus 5 would be -11. 4 negatives would give me a positive. See, same thing, f of -3. Don't forget to add it to your number line. F of -3 is equal to -3 plus 2 is -1. -3 minus 2 is -5. Over -3 plus 5 is 2. And -3 minus 5 is -8. So 3 negatives would give us a negative. Then f of 0, this one's the best because you just get to pull all the numbers. So 2, -2, 5, and -5. Even amount of negatives, so that one is positive. Then f of 3, 3 plus 2 is 5, 3 minus 2 is 1. 3 plus 5 is 8, but 3 minus 5 is -2, which would give us a negative. And then last but not least, f of 6. 6 plus 2 is 8. 6 minus 2 is -8. Not -8, sorry. 6 minus 2 is 4. See, this is why you shouldn't do all your math in your head. 6 plus 5 is 11, and 6 minus 5 is 1. All positive would give us positive. Now, don't be fooled, just so you don't get used to this. They're not always going to switch off like this. I know your first 2 examples did, but we don't want to get into the habit of thinking they're just going to switch off. Okay, now we're looking for less than, so that's going to be our negatives. We're less than from -5 to -2, and from 2 to 5. And of course, parentheses, because we don't have an equals to, we wouldn't include any of these even if we wanted to. And that is our solution. Okay. One thing I do want to note, I saw a lot of errors with this with our polynomial inequalities. Be careful to not confuse your actual zeros with the numbers you plug in. So maybe my notation isn't working for you. You need to do a better job of keeping it separated. You want to write it on a separate line. That's totally fine. Maybe you don't want to add your f ofs at all to your number line. You just want to keep those numbers so you don't get them confused. But just be careful. That was probably one of the biggest mistakes I saw, is that we did all the right work, but then we got confused with the numbers we plugged in our actual zeros and used some of the numbers we plugged in our interval. So just be careful with that. All right. I want y'all to go ahead and pause the video and do examples 3 through 6. Either on your own if you just want to work independently, or you can work with your table so you have someone else to kind of work with. One thing I do want to note before I set you loose, okay, ones like example 5 and example 6, notice how we have these factors that are squared. That just means we have the same iteration of the same factor, so we just get a single 0 from it. The only thing that's going to change is that when we plug numbers in, we do have to remember to actually plug that number in and then square it, just like it is in the actual equation. So go ahead and pause, do examples 3, 4, 5, and 6, and then I'll go over them here in a bit. All right, y'all, let's go ahead and talk about each of these, make sure we're on the same page. So number three was super nice. Just had the one single zero. So we get x equals 3 as our zero. Setting it up with 3, I picked 0 and 4 to the left and to the right. You could pick really anything. Negative to the left, positive to the right. It is greater than, so we want our positive side, so 3 to infinity. 3 was undefined, but it's also just a greater than, so we wouldn't have included it anyways. Then on example 4, this one's a little wonky with that 4x plus 8, but still fairly simple to solve. We get x equals negative 2 and x equals negative 5. Negative 5 comes from the denominator, so we want to make sure we note it as undefined, and negative 2 is our 0. Plugging in, we get positive, negative, positive. We're looking for less than or equal to 0, so that's going to be our middle, but we can't include negative 5 because it's undefined. We do want to include negative 2 because it equals 0. Then example 5, this is our first one with our squared, and right off the bat, hopefully you notice that you got positive, positive, negative, positive instead of our typical where it switches every time. So that's what those squares are going to do. It's going to do things that are a little bit wonkier to our rational functions. We're looking for when it's positive. And this time, because from negative infinity all the way to 1, we're positive, and we can include negative 2 because it equals 0, we can just make one interval from negative infinity to 1, including that 1. And then from 2 to infinity, but we cannot include 2 because it's undefined. It came from the denominator. And last but not least, example 6, simple like example 3, but not so simple in the solution. So we do get the 1, 0 of 1. Plugging everything in, we get the positive and the positive on both sides, but our inequality was looking for less than or equal to 0. So we're never less than 0, and this is undefined, so we don't even equal 0. So in the case of this specific rational function, there's no solution to that inequality. Nowhere does this inequality ever be less than or equal to 0. So we just get that no solution. All right, last thing I want you to do is example 7. This time I flipped it on its head. I've given you the picture of this rational function, so it's everything we've been doing kind of algebraically, but now you actually have the graph to it. And I just want you to answer each of these inequalities. So when is the function less than or equal to 0? When is the function greater than 0? And when is the function greater than or equal to 1? Go ahead and pause me, and then you can check your work here at the end. All right, y'all, checking in on our last part. We can see that when is it less than or equal to 0? So that's going to be when it's below that x-axis. So from negative 3 to negative 1, and we can include negative 1 because it does equal 0 there. And union with 2 to 3 is when it dips down back below. Once again, I can include 2 because we do equal it, but I don't want to include 3. I don't want to include negative 3 because that's where my asymptotes are. Then greater than 0, this one's a little sneaky because we have this negative infinity to negative 3. Then we have this little piece right here, negative 1 to 2, that we need to include as well. And then from 3 to infinity. All of those are above the x-axis, so all those need to be included. And you can see when we're talking about those undefined, these are those undefined asymptotes that are creating those spots where we can't equal, even though maybe we should be able to equal them. And then see our last one, f of x is greater than or equal to 1. So as opposed to it just being above the x-axis, it's above its horizontal asymptote of 1. And that's just going to be that negative infinity to negative 3 and 3 to infinity. All right, that is rational inequalities. They are fairly straightforward, kind of an extension on our polynomial inequalities. Go ahead and try some practice on your own, okay?